online. Okay, let's get started on time.
Yeah.
Okay, so good afternoon, everyone. Welcome to the Penn State CTSI BERD seminar series. My name is Lan Kong. I'm the co-leader of Biostatistics, Epidemiology and Research Design core of Penn State CTSI. So myself and my colleague Jay Zhu will be organizing the seminar series this semester. If you have any questions, feel free to email us. As you can see, our seminar series is set up as the Zoom webinar, which is being recorded automatically. You are muted. However, you can submit questions through the Q&A box. For those who registered for the seminar, you will receive the presentation slides after seminar. So when you close the Zoom session today, you actually will be asked to take a brief seminar survey. So now I'm very pleased to introduce our seminar speaker today, Dr. Vernon Chinchilli. Dr. Chinchilli is Distinguished Professor and the Chair of Public Health Science from Penn State College of Medicine. He has over 40 years of experience in the design, conduct, and analysis of multi-site clinical trials and longitudinal cohort studies. Dr. Chinchilli has served as the principal investigator of many NIH-funded data collection centers. He has published widely in the medical and biostatistical literature with over 300 peer-reviewed publications, especially in the areas of clinical trials, longitudinal analysis, crossover trials, and meta-analysis. So now, without further ado, I would like to turn this over to our speaker, Dr. Chinchilli.
Thank you, Lan. Thank you, Jay. So let me share the screen. So good afternoon, everyone. So today I'm going to talk with you about cluster randomized trials. So in most randomized clinical trials, we typically are randomizing the individuals to the control and intervention groups. As the name suggests, however, in cluster randomized trials, we're going to randomize clusters of individuals at one time to control and intervention groups. So different examples of clusters, and you'll see all kinds of applications of this in the literature. Clusters could be hospitals, they could be clinics or medical practices, schools, factories, even geographic regions. Can be cluster randomized. So the first key feature you have to keep in mind is that within a cluster, there tends to be a correlation. Within most of our statistical analyses, we usually assume that all our participants are independent of one another. That's the basis of our statistical test that we typically apply. With a cluster randomized trial, however, there tends to be some level of correlation within members, within individuals, within a cluster. So we need to keep this in mind when we do our statistical analyses of the data from a cluster randomized trial. The second key feature is that the sample sizes of the clusters tend to be large. So the trial may consist of a small number of clusters. And towards the end, the latter part of the presentation, I will talk about some sample size issues with cluster randomized trials. So there's three main reasons for considering and invoking a cluster randomized trial for a clinical trial. One, the intervention has to be applied to an entire cluster, or it's just more convenient to do it in that manner. The second one really is important, and I've seen this happen on a number of occasions. The investigators might be worried about contamination of the interventions within a cluster if the study participants are randomized individually. So what that means is individuals talk to one another, and they may learn, especially if it's not a blinded placebo type of intervention as the control. Individuals learn about what their colleagues are doing, their classmates, their family members, relatives, friends, whatever, who also might be involved in the study. They learn about that, and it contaminates them. If they're randomized to placebo or to some control, they may learn about what the actual intervention is and may actively participate in that intervention. So many circumstances, the researchers are worried about this type of contamination of the interventions. And so that's why cluster randomization might be more appealing in that circumstance. And then the third reason is the study objective is to estimate population level effects of an intervention administered to a large portion of the population. So one of the references I'm using here is a book by Hayes and Moulton from 2009. The book is entitled Cluster Randomized Trials. And I have the references on the last couple of slides if you get the slides and want to look up some of these references. But anyway, one of their examples is called the post-trial. And in this particular study, there were 52 medical practices in which the investigators randomized them to intervention and control. 25 practices were randomized to intervention, 27 were randomized to control. They had a total across these 52 medical practices, a total of 328 patients with coronary heart disease, right? And a little bit more about this study. Each participant had been hospitalized due to myocardial infarction or unstable angina. Those participants assigned to the intervention received mailings every 2 weeks, at 2 weeks and then 3 months after hospital discharge about methods to reduce the risk of future cardiovascular events. Those participants who were assigned to the control did not receive any mailings after hospital discharge. The investigators decided to randomize the medical practices to intervention and control instead of randomizing the individual study participants. And the main reason for this was contamination. They were concerned about contamination. And in particular, they're worried that study participants within a medical practice would discuss or share their materials with each other. So that was their primary reason for resorting to a cluster randomized scenario. So as I mentioned previously, individuals within a cluster tend to be correlated with each other. A lot of times it's a small correlation. We're not talking about some huge correlation, but even a small correlation can have some impact on the validity of your analytic results if you don't account for it, right? So again, this correlation tends to be positive and tends to be small. I say here, I've never, a negative correlation is rare. I've actually never seen that occur in a cluster randomized trial. Doesn't mean it can't happen, but I just haven't seen it happen. So another example from the book by Hayes and Moulton, this is hypothetical data. Now, this is somewhat contrived, but it does get across the concept. So they made up these hypothetical data from 2 different cluster randomized trials. We'll call them Trial A and Trial B. Each trial consisted of 10 villages, with 5 of them randomized to control, getting no health education, and 5 randomized to intervention, where there was health education. And the outcome variable measured on each child in this study who was enrolled was the presence or absence of diarrhea. So here's a little table from their book on these two different trials, right? So the first thing you should notice when you examine this table is that the control and intervention rates across the villages are the same for the two trials. So in other words, in trial A, there was 10% of the children with diarrhea. In the control, in the intervention villages, there was 6% rate of diarrhea. If you examine trial B, you'll see overall the percentages were exactly the same, 10% and 6%. Okay. So if you did a typical analysis here, like a Fisher's exact test or a chi-square test, just on 5 out of 50 versus 30 out of 50 here, and likewise 5 out of 50 versus 30 out of 50, you wouldn't get anything statistically significant. You would get statistically significant. You get a p-value of 0.03 comparing 10% to 6%, regardless of which trial you were examining. However, that doesn't account for what's happening within each trial, within the villages. If you examine trial A, you'll notice that in the control villages, the rates range from 8% to 12%. In the intervention villages, they range from 4% to 8%. So there's less variability across the villages, first for the intervention and then for the control. When you examine trial B, though, you'll notice there's much more variability across villages. In the control villages, the rates range from 4% to 16%. And in the intervention villages, the rates range from 0% to 12%. And actually, it's easier to see that variability when you look at a graph. So here are the percentages in the 5 control interventions from trial A. Here's the 5 percentages from the intervention in trial A. And again, you can see there's not as much variability as there is in trial B for control and intervention, right? So we want to account for that. So we would do analyses that account for that type of variability that you see across the villages, right? And in fact, when you do the appropriate analysis, you get that trial A, there is a difference between intervention and control. The p-value is 0.02, whereas for trial B, where there's much more variability, it shouldn't surprise you that there was not a statistically significant difference between intervention and control when you do the correct statistical analysis. So again, although that was a contrived example, I think it really illustrates what can happen in a cluster randomized trial. So I do need to introduce a little bit of terminology. I tried to keep this to a bare minimum. I'm not going to go into great depth about statistical modeling, but I do want to describe a few terms that we'll be using, all right? So first, let's talk about the measurement themselves. So Y will indicate that that's the outcome variable measured. Notice I have 2 levels of subscript here. So J is going to represent the participant and I is going to represent the cluster. So I'll assume there's a total of capital C clusters. And within a particular cluster, the number of participants will range from 1 to all the way up to M sub I. So notice that I'm allowing for the fact that there could be different numbers of individuals from one cluster to another. In the previous example, since it was contrived, that didn't happen. There were 100 participants in each village, regardless of what trial you were in. But in general, we have to allow for the fact that you could have different numbers of participants within each cluster. The two important measures we're going to have are sigma b squared and sigma w squared. So sigma b squared is going to denote the between cluster or intercluster variance. And that's what's being described here in this figure. We're looking at here in trial B, we're looking at the between cluster or intercluster variability. So I'll denote that as sigma b squared. Sigma w squared will denote the within cluster variance. So how do the individuals within a cluster, how do they vary from one person to the next? So we have two sources of variability in a cluster randomized trial, and we need to consider both of those sources when we're doing our analysis. So the total variance on an individual comes from these two sources. So the variance for the jth participant in the ith cluster is going to be a sum of these two sources of variability, the between cluster variance and the within cluster variance. So why is that important? Well, it's going to lead us to something called the intra-cluster correlation, the ICC. Right? So first, the intra-cluster covariance between any two members in the same cluster. Notice here, I'm looking at the covariance between Yij and Yik. So these are two individuals, J and K, from the same cluster. So their covariance is going to be sigma b squared. They're related to one another simply because they're within the same cluster. So all I'm doing next then is just converting the covariance to a correlation, right? So that's typically we use the Greek letter rho for correlation. So rho with a subscript of ICC, that's going to represent the intra-cluster correlation. So it's simply the covariance divided by the product of the square roots of the variances. And if you do the simple algebra here, you end up with this being the expression for your intra-cluster correlation. It's the between cluster variance divided by the sum of the between cluster variance and the within cluster variance. So this is probably what you really need to remember more than anything in terms of the notation I've given is this expression for the intra-cluster correlation. It's going to have a big impact on the analysis, and also when we're planning a study, we need to make a guess of the intra-cluster correlation to do a sample size calculation. So we'll get to that eventually. So a few more issues. So in general, cluster randomization yields less precision, more variability in estimating model parameters like the means between your intervention and control or whatever you're trying to estimate. You're going to get much more variability than you would with individual randomization. And hopefully I made that clear because you have two sources of variability. In your typical study with individual randomization, you only have the variance on the individual. With a cluster randomized trial, we have two sources of variability. So it shouldn't surprise you, there's more variability that's inherent in a cluster randomized trial. More variability translates into you're going to need a larger sample size, right? Now, this increase in the variance due to the cluster randomization is what statisticians call the design effect. So I'll designate it in this manner, but I'll just call it the design effect. And it's simply the ratio of the variance based on cluster randomization to the variance that you would have if you just did individual randomization. Right? So why is this important again? Well, it's going to impact your sample size calculation. Right? So the sample size for a planned trial, if we at first consider a continuous outcome variable, we'll make assumption typically that it's normally distributed. We'll assume that the sample size for a trial based on cluster randomization actually can be determined as the design effect times the sample size for a trial based on individual randomization. So for example, suppose we determine based on our assumptions and preliminary data we might have, suppose we determine that the design effect is 1.5. Right? We'll look at an example later on, but just for the moment, I'm pulling this out of thin air. And let's just assume we've done some work and have that the design effect will be 1.5. And suppose we did a sample size calculation under the assumption of individual randomization. And that sample size calculation said we needed 120 participants in our study. If you then decide that you're going to perform a cluster randomized trial where the design effect is 1.5, then that means the sample size you will need for the cluster randomized trial will be 1.5 times 120, which will be 180. Okay. All right. So how do we determine this design effect? So I'm going to spare you all the statistical development of that. If we make a simplifying assumption that all the cluster sample sizes are the same, when you're planning the study, it's easy to make that assumption, but when you actually carry out the study, it's unlikely to happen. But let's assume that the sample sizes for all our clusters will be the same when we're planning the study. So in other words, I'll call that sample size M. So each cluster will have M individuals. Then we get a nice result for an expression of the design effect. It's simply 1 plus this cluster sample size minus 1 times the intra-cluster correlation. Okay. So typically what I've observed and what you see most often is that this intra-cluster correlation ranges somewhere between 0 and 0.2. Occasionally, you might encounter a study where it's larger than that, but most of the studies, cluster randomized trials I've encountered, this intra-cluster correlation ranges between 0 and 0.2. So, but even in that situation, if M is relatively large, if the number of individuals within a cluster is large, notice that's going to give you a large design effect. So for example, suppose your intra-cluster correlation wasn't too big, it was 0.05. But suppose you were planning on having 50 individuals within each cluster. Well, just doing the basic arithmetic here, you'll get that your design effect is 3.45, right? So if your sample size calculation says you needed 100 people if you were doing individual randomization, but if you then decided you would do a cluster randomized trial with 50 individuals within each cluster and where the intra-cluster correlation is 0.05, then you would need 345 individuals to recruit for your study. So In a cluster randomized trial, try to remember it's better from the sample size perspective to have more clusters with a small number of participants per cluster rather than having fewer clusters with a large number of participants per cluster. Okay. Now what happens, that was under the assumption of having a continuous outcome variable, somewhat normally distributed. A lot of instances in your cluster randomized trial, the outcome might be binary, right? In such a situation, we don't have an explicit or obvious expression for the within subject variance, the within cluster variance. So one approach that we've resorted to, and you don't have to worry about this so much how we derived it, but if you assume a latent variable that's continuous, that follows a standard logistic, and construct your binary random variable from it, what we get, we can derive mathematically an expression for the within cluster variance, and it turns out to be pi squared over 3. So we can still use this expression for the design effect on this slide, even when we have a binary outcome, and where we can use this to try to come up with an expression for our intra-cluster correlation coefficient. Okay. Now, there is a consort statement. I'm sure many of you who do clinical trials or involved with clinical trials are familiar with the consort statement on how you should report the results in your manuscript from a randomized clinical trial. There turns out that in 2012, some of the consort personnel developed a comparable statement for a cluster randomized trial. Again, the reference is in the last few slides. So these authors, we'll look at it briefly. They have a check similar to the standard consort statement. This consort statement has a checklist on how you should report the results from a cluster randomized trial. I want to point out a few of the unique features. Now you have to remember that these authors were British, so they're using the British spelling of randomized. In the title, your title of your manuscript should indicate that it's a cluster randomized trial. In the introduction, you should have a rationale for why you're using a cluster randomized design. Also in the introduction, you should indicate whether your research objectives were for making inference at the cluster level or at the individual participant level, or both. In the section on trial design, you should define your clusters and describe how they design features apply to the clusters. You should describe the eligibility criteria for the clusters. And then this isn't that different from the standard consort statement. You do need to describe the interventions and whether the interventions pertain to the cluster level, to the hospital or clinic, whatever, or they're actually applied at the individual participant level. Sometimes it's a combination of both. And then likewise for the outcomes, are they measured only at the cluster level, or are they measured at the individual participant level, or both? Additional requirements from this table and the consort statement: how you did the sample size calculation, what you assumed about the intra-cluster correlation coefficient, how certain or uncertain you are about, are you using prior data? Are you just making your best guess at what that intra-cluster correlation coefficient might be? how you performed randomization, specifying whether randomization was based on the clusters rather than individuals, how you manage concealment of the randomization up until the time of randomization, and then other logistical information, who generated the random allocation sequence, who enrolled the clusters, et cetera. Okay. More detail about randomization, and of course, your statistical methods, how you're accounting for clustering in your statistical analysis. And then in the results, report the number of clusters that were randomly assigned, received the intended intervention, were included in the analysis for the primary outcome, describe for each intervention and control group, losses and exclusions for both the clusters and the individual cluster members. Maybe I'm beating a dead horse here, but more information about what you should include in the results section. And then finally, in the discussion section, the generalizability to clusters and or individual participants as relevant. So here's, this is table 2 from that article. We're not going to go through this. This is too difficult to read and tedious, but it does give you some guidance as to how you should address those issues when constructing your manuscript. So it's a very good article, but you know, it is part of the consort family of articles. So it's highly recommended if you have a cluster randomized trial that you follow these guidelines in writing your manuscript. Okay, let's talk about some more examples. All right. So this was taken again from Hayes and Moulton's book. So this was a cluster randomized trial, which was performed in northern Ghana. And the researchers partitioned the area of study into 96 geographic regions of interest. These ended up being the clusters. And they randomly assigned 48 of them to control and 48 of them to the intervention. And the intervention was the use of bed netting for children when they were asleep. The primary outcome variable was child mortality, measured as time until death during a 2-year follow-up period. They had some covariates they adjusted for, female status, and age in months at the study enrollment. At the end of the study, when they had all the data, they applied a proportional hazard regression, since their outcome variable interest was time until death for the child. And they had a random effect for cluster within their proportional hazards regression model. So that would account for the cluster to cluster variability. And the estimated hazard ratio that they reported was 0.84 with a 95% confidence interval from 0.73 to 0.99. So they had a statistically significant result in that the intervention of bed netting significantly reduced the child mortality compared to the control. Another example from Hayes and Moulton. This was a cluster randomized trial that was performed in Scotland. The researchers randomly assigned 25 schools to control or intervention. And the intervention here was sexual health education. And the primary outcome variable was a knowledge score that ranged from -8 to +8. Covariates included sex, male or female, and the parents' social class. And they had 6 levels for social class in Scotland. They applied a linear mixed effects model so that they could estimate the between cluster variance and the within cluster variance. And what they got was that the between cluster variance was 0.12, the within cluster variance was 5.06. And so when you use the expression here for calculating the intra-cluster correlation, it was, I forget the numbers already. I remember sigma W squared was 5.06 and sigma B squared was 0.12. So anyway, when you do the arithmetic, you get that your estimate of the intra-class correlation was 0.02. So not large, but a small positive one. And it was useful in the analysis. So there was a statistically significant increase in the knowledge score for the intervention. Okay. Another example, this time, let's do a sample size calculation. Right? So an investigator wanted to determine the sample size for comparing two asthma therapies with respect to FEV1, the forced expiratory volume in 1 second. The investigator was planning a two-sided 0.05 significance level, wanted to have 90% statistical power. And the effect size that the investigator wanted to detect was a difference of 0.25 liters between the two therapies. And using reports from previous studies in the literature, the investigator estimated that the standard deviation was 0.75 liters in a similar population of people with asthma. The investigator wanted equal allocation between the two treatment groups, did a sample size calculation, and came up with a number that he needed 191 people for each of the two groups for a total of 382. So this first paragraph here was a sample size calculation that was performed under the situation with a individual randomization. Suppose now the investigator changed his mind and decided that he would pursue a cluster randomized trial and that he would recruit clinical centers and randomized clinical centers to each of the two asthma therapies, right? And that it was reasonable to expect that each clinical center could recruit 30 participants. Let's assume we had some data or some prior information, and we came to the assumption that our intra-class correlation would be 0.025. So what is our design effect? Well, again, it's 1 plus M, and M in this case is 30 participants per clinical center. So that would be 1 plus 29 times the intra-class correlation coefficient, which we're assuming is 0.025. So our design effect is 1.725. So for the cluster randomized trial, the researcher would need 659 individuals, 1.725 times 382. That was calculated up here. So that's roughly 22 clusters. So because 22 times 30 would give you 660. So that's just an example of a sample size calculation, again, resorting to this design effect to try to determine the sample size. Okay. I'm going to move on to a different type of design, and maybe you're familiar with this, and maybe you're not. It's called a stepped wedge cluster randomized design. In this situation, it's somewhat different, okay? You're still going to randomize clusters, but in this type of design, every cluster eventually will receive the new intervention. And the randomization process determines at what point in time each cluster is going to start the new intervention. So this is in contrast to the standard cluster randomized trial that I described previously. There, you would just randomize a cluster to receive either intervention or control. In the stepped wedge, every cluster is going to get the intervention. The issue is, when will they receive the intervention? So it's called the stepped wedge. If you look at this illustration here. So here's a situation where we're going to have 12 clusters, and we have, you'll notice, different phases of the study design. I labeled them phase 0, phase 1, up through phase 6. Okay. And what we're going to do, or in this contrived example, you'll notice at phase 0, all 12 clusters are using the control. Right? Yellow corresponds to the control intervention, blue corresponds to the new intervention. So what you're going to do at some point after phase 0, after a period of time in which all 12 clusters are using the control intervention, you're going to randomize 2 of the clusters in phase 1 to start on the new intervention. After a period of time, you're going to reach phase 2, and you're going to randomize 2 more clusters to start on the intervention. And once in the step wedge, once you start on the new intervention, you'll notice that you stay on that cluster stays on that new intervention throughout the remainder of the study. So you just keep doing this until you reach the final 2 clusters that they start on the new intervention at phase 6, at the very end. Right? So it's called the stepped wedge, as you can see, because of the appearance of this particular diagram. So why would we consider something like this? Well, the first is there is a practical issue to consider. What are you going to do within a cluster? Suppose a patient or a participant is enrolled. So suppose they're in cluster 4. And suppose in cluster 4, they're going to start on the intervention when phase 2 begins. Well, suppose someone, a patient or participant, is enrolled at the very end or close to the end of phase 1. So that particular individual overlaps phase 1 and phase 2. What do you do with that individual? If they started out on the old intervention, the control intervention, do they remain on that in phase 2, or do they transfer over or cross over to the new intervention? So there are some practical issues like that that the investigators need to address with a step wedge type of design. But what are the advantages of this? Well, the obvious advantage is that it's appealing to your clusters because eventually all the clusters will undergo the new intervention. So you're going to have more willingness or eagerness to participate in your cluster randomized trial. An article by Hemming and colleagues showed that there's also a statistical advantage with the stepped wedge design when there's an appreciable amount of intra-cluster correlation. So those authors did some computer simulation studies to arrive at that conclusion about the statistical advantage. Okay. So here's a hypothetical example. So a group of investigators conducted a step wedge cluster randomized trial. They recruited 8 sites and planned for a baseline period along with 8 active periods. All 8 clusters used a control intervention during the baseline period and were randomized to the period in which they initiated, period or phase in which they initiated the intervention. The outcome variable was continuous and normally distributed. What they discovered, remember, this is contrived. The control mean was estimated to be 4.9. The intervention mean was 5.5, and they were statistically significantly different using an appropriate statistical model. The estimated intra-cluster correlation coefficient in this data was 0.08. So, to my surprise, the consort family even developed a consort statement for stepped wedge cluster randomized trials. I've included table 2 from the article, this consort statement, on some of the key methodological issues you need to describe when you're reporting on a step wedge cluster randomized trial. And then there's another table in the consort statement with the actual checklist. Now, not everybody is enamored with cluster randomized trials. Kotz and colleagues published 2 articles in 2012 where they describe why they don't like the stepped wedge cluster randomized trial and that they recommend not invoking it, right? So again, the references are at the very end if you're interested in seeing them, reading why they said this. In general, they just thought there were too many practical issues that are somewhat addressed in a nebulous manner with a stepped wedge cluster randomized design. They thought it was much cleaner and you'd have less bias with a standard cluster randomized trial compared to a stepped wedge cluster randomized trial. They admit there are some circumstances where it might be feasible to apply a step wedge design, but in general, they were negative about it. Okay, so actually that's the end of my presentation. And as I said, there's a couple slides with references in case any of you want to look those up. So we do have some time, 10 minutes or so, to address any questions. So let's see, one in question and answer.
Yeah, there is one in the Q&A.
Okay, so yeah, one question was, can you give examples of positive and negative correlation in cluster randomized trials? Well, as I said earlier, I've never seen one with a negative intra-cluster correlation coefficient, but I guess you could theoretically have a negative correlation if individuals within a cluster interacted in such a way that one person responding positively to the intervention, the other one would respond negatively. I mean, it's really hard to think of a situation like that. But theoretically it could happen. It's just that I've never seen anything like that happen. Typically, you do see a positive intra-cluster correlation, that the individuals within a cluster, either because the way the physician administers the intervention or the way the physician interacts with the individual participants, there's some sort of common thread there so that individuals within a cluster, there's a small tendency for them to respond in a similar manner. Okay, there's a second question. If we compare individual and cluster randomized trials, would they yield the same or similar result for the primary outcome? Well, theoretically, you would hope so. But in actuality, it's hard to say. Every situation will be different. It's possible that in the cluster randomized trial, because you're accounting for physician effects, in terms of the cluster, it's possible because of the higher variability, even though you have a larger sample size, you still may not detect a statistically significant result, whereas with the individually randomized trial, you possibly could, just because you're overlooking some source of variability. So yes, it's not necessarily true that you would get the same results with both types of trials if they were examining the same research question and sampled from the same patient populations. The third question, is time effect a negative concern for the stepped wedge design? It could be, that's true. A lot of times with the stepped wedge design, you'll see it used more as a process control type of study, where say a hospital or a clinic has a new process that it imposes, that it starts to use. And so you're taking measurements at the cluster level and not so much at the individual level. It's possible that, yes, over a period of time, as the cluster gets accustomed to that intervention, that there is a time effect. And so you should try to account for that in your statistical model for the stepped wedge design. There's another question. Investigators often do not have estimates, assuming no pilot or previous publication data, of things like the ICC or the design effect. That's true. What I've done, and I've encountered that situation, what I've done typically is calculate the design effect under the assumption of a intra-cluster correlation of 0.025, 0.05, and 0.10. And so look at a range of sample sizes that I get under those different three scenarios. Now, obviously, I'm going to get the largest sample size with the intra-cluster correlation coefficient of 0.10. So then I typically rely on the investigator to tell me, to try to give some rationale as to maybe 0.10 is too high. They wouldn't expect something that high, or maybe 0.05 is more reasonable. So it is difficult when you don't have prior data or prior information as to trying to make a good guess for the intra-cluster correlation coefficient. I think I covered everything so far in the question and answer.
So Vernon, I have a question. You mentioned the design or the sample size calculation depends on the objective of the study. It pertains to cluster level analysis or individual level analysis.
Right.
So if the primary outcome of interest is the aggregate outcome, cluster level outcome. So maybe the individual level is really difficult to obtain.
And that's possible, that's true. In a lot of these quality control interventions that a clinic or a hospital may implement, yes, a lot of times It's at the measurement, the primary outcome variable is at the cluster level. And that could be expressed, say, as, percentage of hospital infections that have occurred during a period of time. So yes, I mean, you have less data. If you have an aggregate measure for what's happened in the cluster, you certainly don't have as much data. You're reducing it to one measurement per time period for each cluster.
So in that case, do we still consider the study is a cluster randomized study, or it's individual is here is basically the cluster, right?
Yeah, I mean, it's to your advantage to try to get your outcome variable measured on individuals. You're just going to have more data. Sometimes, as I said, that may not be feasible, depending on what the research objective is. And so you may just have a rate for the cluster or a percentage for the cluster during each time period. So yes, your data will be much more sparse. And so you're not going to have a lot of statistical power unless you have a large number of clusters. Look, there is one more question here.
Oh, that's a thank you.
This
No.
is the thank you.
Any other question? Okay, no more question. Okay, so we are ready to close our seminar session today. Thank you everyone for joining us. Thank you, Dr. Chinchilli, for giving us such a great talk. So our next seminar will be in 2 weeks from now. The topic is on randomization and the sample size estimation. We look forward to seeing you in our next seminar. Thank you.
Okay.
Thank you, everyone.
Bye-bye.
Thank you, everyone. Bye.